So we started to graph, and I guess that's exciting part of the story. So I can graph something like exercise number 80 that deals with a graph of a circle that has radius equal 4. Circle with radius 4 will be graphed like that, 4 for the radius. So we have a very neat way to describe circular like relations. It's not a function. And we also know that x squared plus y squared is equal to a square of radius, simply because if you were to take a look at the point, at any point on the circle, then x coordinate will be here, and the y coordinate will be, as usual, on the y-axis. And you're gonna be able to see that if I magnify this a little bit. So the x is one side, y is the other side. Of course, this is 90 degrees angle. It's a right angle because perpendiculars. And this is radius. So it's just another way to write down the statement of Pythagorean theorem. And therefore, instead of r, I can put down a square root from x squared plus y squared, right? And this is equal to 4. So it's a way to rewrite this in more familiar form for us, which is a form of xy coordinate plane rather than polar. So you can see that standard equation of circle, which is sum of x and y squared is equal to a square of radius, is here, and it doesn't look as nice as the actual equation on polar coordinates. So that's what they're asking us to do. And of course, with a circle, everything is nice, but with problem like 81, it's not as nice. So let me do it. 81. They actually don't ask to graph. They just ask to write it with x and y coordinates, and that's it. But I think the graphing is always exciting part, and that's actually why we're doing this. We're trying to produce pictures of these relations in the next section. So when I have equation in this form, in the problem number 81, of course, the part that bothers us is denominator. So I'm gonna multiply by this denominator on both sides of my equation. So it's gonna cancel on the right, and this is gonna appear on the left side, right? So cancel this. And then I'm gonna also distribute this r over, so we don't have any parentheses. And this will enable us to actually write what we have for the equation, r minus r times cosine theta is equal to 4. So if you wish to replace these with x and y's, need to recall that our x coordinate is r times cosine of theta, and that's actually what we have here. So I can say that this is x, which is subtracted from r, and instead of r, we just utilized the expression here, so I can extract the square root from this x squared plus y squared, right? And this is our equation. In fact, if you try to get rid of the square root, so if you do a little bit of algebra here, so you get this square root isolated first, and then you bring this x over to the right side. So then you can square both sides of this. It's not needed, it's just trying to show that we usually try to write this in a little bit better shape. In fact, isolate y is what we usually do, right? So we get no square root on the left side, and on the right side, if I square this parentheses, I'm going to get 16 plus 2 times 4 is 8 and times x, and then plus x squared. And what you're going to get is that x squared that will cancel, right? Because you subtract the same thing on both sides. And you end up with a way to produce expression for y, which is going to be just a square root from this 16 plus 8x. So probably that's something that you may recognize. It's analog of a square root function, right? So this will be a something that we can graph. If you remember the graph of a square root of x function, it looks like that, half of parabola. So analogously, I could graph this one, which is going to be dealing with its domain. So we got the 16 plus 8x, which is not negative, because otherwise you cannot extract the square root. It may be equal to 0 as well. So you can see that 8x is greater than or equal to negative 16, and x is greater than or equal to minus 2. So then the graph of this will be starting at minus 2 and resembling a shape that half of the square root function. So definitely this is much nicer to turn into the xy equation rather than polar coordinates, because it's just going to be a mess to deal with graphing the square root function in polar coordinates, turns out. But if you write x and y coordinates, then I'm thinking that you're an expert in graphing, right? With xy coordinates, we've been doing it throughout all of the math classes. So in the next section, they talk about more of these graphings. So I just tried to open the door into it, and actually all the graphing occurs here in the next section. For example, if you look at the second example with angle theta equal to pi over 4, means that r is any real number, right? Because they don't tell you what r is. It means that r is anything. So r could be 1, could be 2, could be just about any point on this angle. And remember, r can also be negative because it's any real number. So r could be -1 or -2, and that will go the opposite direction, right? So that way you have the graph of line through the origin. You just describe it with angle. And that's, I think, interesting to realize, right? So graphs of various things, and sometimes you can even get a graph of the line. And they describe those lines, and I guess the key idea is not to get into graphing of lines, but to get into graphing of various equations in circular-like shapes. And that's what they're doing here. So like, for example, you can see here the graph of this so-called cardioid, the favorite graph for the medical workers, the cardioid, which looks like a heart. So you can see it's here, and then it just extends around. And the way they graph it is they use points. So they use points, and they can just follow through the way they do this, and then we'll graph one on our own. So the graph is here, r is equal to 1 minus sine of theta. And the way they do it is they plot a few points here. So they calculate them in a table 1. So they take various values for angle theta. So they say, what about if theta is minus pi over 2? Well, then they plug it in the equation here. So it'd be 1 minus, and then sine of that negative pi over 2 is minus 1. So with another minus, it'll be plus. That's how they get 2. And then they plot this point using the r equal to negative pi over 2. So the angle should go down here, right? Negative pi over 2. And then they take 2 steps, and that's going to be the point. Then they take other values for angle pi over 3 and so forth. I'm interested in value 0, so that's equal to 1. When you get that sine of 0, it's 0, so you just have 1 left. So when angle is 0, so it should be going in this direction, right? Then we have 1 here. So notice it's like half shorter than we used to have. And it turns out then you can connect these with continuous graph. And that's where these two values are coming from, to justify that if you have angle pi over 3 with minus sign, then your value for the r is going to be a little less than 2. So it used to be 2 steps, now it's a little less than 2. So they're trying to show that when you get angles that start to be closer to the 0, then the 0 angle is here, then the value of r gets smaller. Like here it's 3/2, and then at 0 it gets 1. And then turns out when you get the angle pi over 2 exactly, it's again 0. So the way that goes, it just keeps getting closer and closer and closer to this point, and then it hits it when angle is pi over 2. When you get this angle, and then turns out on the other side it's going to be symmetric, and you get a picture like a heart, and that's what they produce. So it looks like the key points are where we get a largest value, or so-called maximum value of radius, and this is 2, and that happens when angle is pi over 2, and the minimum value of r when it is equal to 0, right? The lowest value is 0, and that happens when the angle is pi over 2. So those are 2 key values that I will be looking at, minimum and maximum. And also it's helpful to know when angle is equal to 0, because usually it's easy to calculate values of sines or cosines when r is equal to 0. And that will be my plan of graphing for all of the relations given in this section. So I'm gonna now take one exercise and do it. And this graphing process is a little bit tedious, but I think little by little, our goal will be to get used to this process because it's same for all of the exercises. That's what makes it be kind of straightforward. So I always find when we get a minimum, when we get a maximum, and also when we have a zero for the R, and that's what I will do now. I just need some room here. So let us start with something here, like say exercise number that wants us to graph. So first group, again, just continues the same exact story as in the previous section where we were turning into XY containing equation. And well, we already did those. All you care about is those sines and cosines turn into X and Y. I can do one, let's say, how about 21? It says R is equal to 2 cosine theta. So the way we do this conversions is we use two formulas. So we know that X is equal to R cosine, we already used it today. And its friend Y is R times sine. So whenever I see cosine, then I notice that R is missing, and therefore I'm going to times by R on both sides of my equation, so that R cosine will become X. So that's a standard trick in these exercises. And here's we have R squared, and we already know that X squared plus Y squared is equal to R squared, Pythagorean theorem. So this will be X squared plus Y squared then. And then this number 2 is the only thing that is left, right? So just copy it. So 2 is here. And we already transformed this into the equation, and start from there. You can graph, but they don't ask. So I'm not going to graph it because sometimes there's too much work in graphing. Let me just get something that they want to actually graph, like number 37. So in this exercise, I'm going to follow the plan of finding the maximum and the minimum endpoints when R is equal to 0 also. So equation here is R is equal to 2 plus 2 cosine theta. So the equation is graph it. And in order to graph, I'm going to find what value of maximum is, what value of minimum is. And looks like minimum will be 0 anyways, because cosine of theta always varies in between plus and minus 1, right? So the largest value is positive 1 and the smallest is negative 1. So when cosine is equal to 1, looks like we have maximum, and maximum will be 2 plus, instead of cosine I put 1, so it'll be 2 plus 2, which is 4. That's largest value. And it occurs when cosine theta is equal to 1. So when cosine is equal to 1, for what angle? Remember, angle is 0, right? When theta is 0, then cosine of 0 is equal to 1. So that corresponds to this point on the circle. So angle is 0. Okay. So when we have a minimum? Well, minimum we have when cosine of theta is -1, right? So cosine is -1 will be at that point on the circle. So that's for angle equal to pi. So when theta is pi, we have minimum. And minimum value is going to be found if you take the -1 and plug into this little equation and see that it is 0. So usually I look for the 3 values of r when it is largest, when it is smallest, and when it is 0, but we already found when it was a 0, it kind of coincides with the value when it is also smallest. So let us plot these points and then decide how the graph should look like in this case. So I'm going to be taking the graph when we have angle pi and the value is 0, and then angle 0 value is 4. So what I do is for angle 0 go 4 units and produce that point. And then when angle is pi, we get to 0. So actually, we're probably going to have something that eventually ends up here. But notice that the angle, it doesn't go here because angle may be bigger. So that's why I can try to get a couple of more values. Let's say when angle theta is something in between, and convenient will be use pi over 2, so I can get r, such as a 2 plus 2 multiplied by, so what's the value of cosine angle pi over 2? It is 0, right? Cosine pi over 2 is 0. You can use a calculator. I like to use unit circle to identify it. And people have their own ways to get, but the point is you can always utilize this. So instead of cosine, any way you like. And r will be 2. So when you have angle 90 degrees or pi over 2, you have value of 2. And you notice it always gonna go smoothly, so it's gonna kind of connect it like that and then go there, and looks like it's a half of the cardioid, right? So probably the other half will be there, so you can verify it if you take the angle, say negative pi over 2. What's gonna happen there? Is that gonna be also 0? And the answer is yes, because at negative pi over 2 is 0. So it's always gonna go nicely and smoothly if we have nice equations like in this textbook, because of course you can always design something that looks nasty and doesn't really go under the nice rules, but we never see those bad ones in here. So I just graphed one of these, the cardioid again, and they say here, match the graph. So do we have something like that? Looks like the last one, right? So I just got H here for matching. It could be nice quiz exercise, but I don't plan to give you a quiz on this because I know it's something that totally different with what you used to see before, right? So that's why I'm gonna do another exercise for you instead of asking you for a quiz. It'll be too much. So let me get something that looks a little bit different than cardioids, because it seems that most of these will be cardioid-like things, and I will try something like number 49. Notice that we have 2 thetas in the parentheses. So let's see what's going to change if we do 49. So I would say this is like the last section that we care about in this class. And maybe if you'd be interested to some people, I can take a look at the next section as well. I think it's pretty neat section also, but we're pretty much done with covering the material. And the next week, we should then have the final. So I would say it'd be good to have a final next Wednesday. I know from experience already that people always forget to turn it in or something happens. So I don't want to postpone the final till the very last week. So this way you will have plenty of time to turn in the final. Moreover, we are pretty much done with covering material. So next class, oh, not we're Tuesday, Thursday. So next Thursday, sorry, not Wednesday. We don't meet on Wednesdays, right? Next Thursday. So on Thursday this week, I will talk more about these graphings and then email you a practice final, just like we did with the midterm. So you will know what to do for the exam. And on Tuesday next week, then I will go over this practice exam and so the standard plan. And then on Thursday, at the end of next week, I will email you the final and just wait for you to send me your work back. And we'll discuss this in very detail next week, of course. So in the meantime, let me do one more problem for you. Was it number 49, I think, right? I'm going to try to do this a little different looking equations because their graphs gonna be quite different than cardioid. So we're gonna continue with graphing some more next time. Because again, this section, I think, requires more time invested. So 2 theta is here. So as usual, I need to figure out what is my maximum, what is my minimum, and when r is equal to 0, turns out. So these 3 things. And maximum will be when cosine of 2 theta equals to 1, right? Because cosine is always varies in between of negative and positive 1. So usually it's either plus or minus. So cosine of 2 theta is equal to 1. We already know when it's theta is equal to 0. But since we're dealing with 2 thetas, then I say that 2 thetas is not just 0, but 2 pi times k. Because to pull out theta, we divide both sides by 2, so you get pi k. And this means that in the region that we dealing with to graph, the region from 0 to 2 pi, we have theta such as either k equal to 0, or it could be also pi. And this is going to give us 3 times 1. Instead of cosine, I put 1, so it's 3. So what are we talking about now? Well, let me start to plot these points. Looks like there are 2 points of interest here. So it's going to be 3 to that point. And on the other side also 3. So that's going to be the largest values for my radius, farthest from my pole. So the next is going to be when it is minimum. And the minimum will be, notice that one can say, is this going to be -1? Well, notice if it's -1, then it's actually going to be what? Sine 2 thetas. Write it down. Is -1. We're going to get a negative value. Would that really be a minimum? And the answer is not really, because that's going to be also r equal to -3. So it's not really a minimum. Our minimum will be when it is 0, but I'll still use that value of -1 here. So it's -3. And now I have analogous equation to solve. So 2 thetas is going to be a pi plus 2 pi k. The period is always 2 pi k. So we're talking about the point here, right? When we have a -1 for cosine. And when I find the angle dividing by 2, I get pi over 2 plus period pi k, right? So what are the values? Well, it's going to be pi over 2 and 3 pi over 2. Or if you wish, you can put -pi over 2. It may be more convenient for graphing, but it doesn't matter. So again, now we're talking about this other 2 points on the unit circle that happens when angles are here. And cosine of those points is -1, so we get radius -3. So how can I graph them? Well, notice that at pi over 2, so angle that goes here, pi over 2, but the r is negative. So we go the other way. So we actually have that going down 3 units. Because again, r is going to be -3 when theta is pi over 2. Remember, it's kind of flipping the other direction. And analogously, when we have a angle minus pi over 2, then I have to, instead of going down, go up because my r is negative. So we got this point. I say, oh, that looks like a circle. No, 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 it's not a circle at all. Those are maximum values. When r is equal to 0? Well, that happens when cosine is 0, right? Because you multiply 3 by 0, so cosine of this 2 thetas must be 0. And this is theta, right? Theta, carefully. So this 2 thetas will be what? Well, looks like the angle has to be pi over 2, right? Plus period. And notice, since this is going to be pi over 2, and then 3 pi over 2, the period is going to be pi to describe this. Pi times k. So to get theta, I'm going to take that 2 away by, I guess it's convenient when you work with fraction that is present in our equation, just multiply everything by 1/2, so you can better see what's happening here. And what's happening, we're going to have pi over 4 plus pi over 2 times k. In other words, our angles will be pi over 4, and then we have, so it's here, here, pi over 2. So if you add 90 degrees, right? Here and here. So there will be 4 angles here. Pi over 4, then I would say 3 pi over 4, and so forth. 5 pi over 4, and finally 7, right? All these pi's over 4. So that's when we get to 0. So when angle is pi over 4, our function goes to 0. Same here. So it goes kind of touching this angle pi over 4, but then at 3 pi over 4, it goes to 0 again. And it goes like that again, and again, and again. So they say it's 4 petal rows. I say, Alex, it's not on the picture. Yeah, because pictures are actually not for us. It's for the group of exercises above. Here they just say graph, and that's it. So this is going to be a so-called 4 petal rows, which is a little bit tedious for graphing, but here's the one that we have. And notice that it deals with a sine or cosine, so it's actually cosine of 2 thetas, and we have produced that graph. That looks pretty different, right? Again, it's not a function, so we never graphed those before, but now we are able to graph some real unusual looking things. So maybe it's a good time to stop with this for today, and this will be the last section for the homework. So now you know what's for the homework. So the next Thursday will be the final. So try to finish up with homework and prepare to send it to me. Or if you already finished with it, you can just email it to me at any time. So I'm stopping recording.